Welcome to the presentation of our paper about IMPAQT Underwater Telemetry Platform with a focus on the receiver design. My name is Hamed and I'm presenting this paper on behalf of Marco Belcastro and Brandon Offley. We are a team working in Tyndall National Institute, and Tyndall National Institute is a research department of University College Cork. And Tyndall vision is being a global leader for deep tech innovation and impact through excellence in research by 2025. We are working in a cutting-edge world-class research center, and we are working directly with industry and EU projects. The main focus of our project are on photonics, quantum, and micro and nano systems, including IC design, smart sensor devices, and etc. And the main advantage of the Tyndall National Institute is to have a diverse community. At the moment, we are more than 500 researchers, and we have 146 graduate students doing research in Tyndall National Institute. We are working in human-centric systems group, where we are bridging the analog and digital world by creating information from the data that we gather from physical world, like from sensors that we are building for cities, for the marine environment, for the agricultural environment, for well-being monitoring systems. And then we get this information, and then we basically use this data and we push the data to the cloud, and we provide services and data to the users. Our main vision is to interface between human and digital domain by developing next generation hardware and software, and we try to keep human in the loop. So we try to inform them how we sustain well-being at work, at home, or in our daily environment. So, for instance, we are trying to give information about the underwater sensors data by developing underwater sensors and developing underwater communication platform, so we can keep humans in the loop to take data-driven action based on the data that we provide to the farmers or to the researchers about the underwater environment. So the problem that we are working in this paper on is basically the communication. So wireless communication is essential part of our life nowadays, and we have it in cell phones, smartwatch, smart cities, and smart sensors. Terrestrial wireless communication, we can say it's easy to do by using some wireless communication modules where you can just pass the information to these modules and they transmit this information for you to a remote location. Then you can retrieve this information from the modules. And this also enable us to develop Internet of Things, where we could have things, smart things, connected to the internet via this wireless communication module. Although when it comes to underwater wireless communication, the communication itself is still challenging due to the high attenuation of electromagnetic waves underwater. And this happened because of the salinity and the conductivity of the water, which reduced the range of a 10-kilometer terrestrial transceiver to less than a meter in underwater environment. Most of the sensors and systems in underwater environment nowadays are using cables or their own communication platform. And there are risks associated with the cables. So for instance, the cables can be chewed by the animals, can get tangled, can stuck in the propellers, or even they can limit the movement of the sensor itself. So these are the problems that we have with the cables. And to just to summarize the problem itself, we can say that there is a lack of general purpose, low-cost miniaturized underwater wireless modem, similar to what we have in terrestrial communication. So in terrestrial, as I said, we have the modules for wireless communication, but we don't have that modules for underwater communication. So in the IMPAQT telemetry platform, we are trying to solve this problem by providing a multi-purpose, low-cost, miniaturized underwater telemetry platform to collect the information, to collect the sensor data, and wirelessly transmit them in real time. So one of the application of our system is aquaculture. aquaculture is one of the main sources of human food and is expected to expand significantly in the future. And with this expansion, there would be environmental impact. So we should be able to minimize the environmental impact of the aquaculture sites, and also we need to minimize the costs to maximize the profits of these sites. To be able to do that, we need to take data-driven actions, and those data-driven actions requires data where we can collect by deploying sensors and monitoring those underwater environments. So, for instance, in IMTA sites where we have multiple species, for instance, farmers combine fed species like fish, shrimp, oysters with extractive species like seaweed and mussels, and then the extractive species will use the byproduct of the fish or feed species. And we need to monitor that in order to minimize the food waste that we are producing, and also we need to monitor the waste or byproduct of the feed species to be able to estimate the amount of, let's say, for example, the extractive species that we need, or we need to monitor the current, the water current, to place the extractive species. We also can monitor various parameters like nitrate, phosphate, sulfate, pH, and oxygen level, which are really important for farming the extractive species and also the fish itself. So this requires development of various sensors and monitor these IMTA sites closely. So in the course of IMPAQT project, which we are working for several years on developing sensors, chemical and physical sensors, and attached sensors, and then we are collecting the information from these sensors through the integrated autonomous data acquisition system and also through the data aggregator system. And then we pass this information along with the remote sensing data, crowdsourcing data, and spectroscopy data through the data storage and management, where we store the data, and then users can use the integrated management system or IMS to obtain this data and to monitor this data. So this enables the user to take data-driven action. And it's important to note that IMPAQT project is part of European Horizon 2020. So, as we mentioned earlier, the IMPAQT Telemetry platform provides a multi-purpose, low-cost miniaturized underwater modem for aquaculture environment, where we attach the transmitter node to seaweeds, to sensors, to even we can keep them floated in the water, or we can connect it to the cage. And then this transmitter node will collect the information from the sensor and then transmit them using acoustic signals to the receiver gateway. And the receiver gateway then transmits data using LoRa to the inland data aggregator. And so to just summarize what we said so far, so in nowadays terrestrial communication, we have sensors and gateways, and they are using electromagnetic waves for the communication. So we have RF transceivers where they transmit the data using electromagnetic waves. But as electromagnetic waves does not propagate well enough underwater, we nowadays the standard communication for underwater is cable. So where we have sensors connected to a gateway via cable, and we are trying to replace that cable in IMPAQT Telemetry platform by ultrasonic acoustic waves, where we have ultrasonic transmitter and receiver, and they are using ultrasonic acoustic waves to transmit the information. So as I said, the IMPAQT Telemetry platform has ultrasonic transmitter and ultrasonic receiver, and the ultrasonic transmitter is basically a board that you can connect to your sensors, and it will collect the information from them and transmit it for you. And basically this will replace the cable and eliminate the hazards related to the cable. And it also easy to deploy the sensors because basically they are wireless, and then you can just put them wherever you want, and then this transmitter node will transmit their information. It also saves a lot of cost related to the cables because the underwater cables are expensive. It also improves the sensor data quality because we are reading the data right after it comes out of the sensors, and this will reduce the noises associated with the underwater environment on the sensors output. It also enables us to have many sensors and just a single point of logging or transmitting. So just imagine in IMTA sites you can have several sensors installed, and then a single receiver will receive information from those sensor nodes. So the IMPAQT transmitter can read data from the sensors through serial communication protocols like UART SPI. It also has optical communication protocol. If required, it can be used, and it can integrate into new devices and system and transmit the information of those devices and system up to 100 meters. It can run for 2 weeks and up to 1 month based on the user configuration, and it can transmit up to 40 bits per second at 42 kilohertz. It also supports the various commonly used modulation techniques. On the receiver side, we have a board that can receive the data that transmitted by the IMPAQT transmitter nodes, and it can log the data, and then like it can log it on the SD card, or it can transmit it to a PC via USB, or even it can transmit it to a remote location via LoRa transceivers. It also supports the onboard modulation to minimize the post-processing of the data that collected. So in IMPAQT transmitter side, when we want to send the data, let's say this is the data, we need to modulate this data to be able to propagate efficiently underwater. So what we do is that we take the data and then we multiply it by the carrier signal, which forms the modulated data, and then we transmit data, this modulated data, underwater. But obviously there would be environmental noise, and signal get attenuated heavily underwater. If you want more details about the transmitter side, you can refer to our published paper in SensorCom 2020. The IMPAQT transmitter to the IMPAQT receiver side has a hydrophone where it can sample the acoustic waves that are presented in the water. And then as you can see here, this information is like these signals are very weak, and they have a lot of noises from the environment. So for the first thing that we need to do, we need to amplify the signal. So here we have a preamplifier, and then a driver, and then these two levels together, these two stages together will amplify the signal, where you can see in figure 2 here. And then we have a filter to filter those environmental noise from the data. And then we have a variable gain amplifier in the system to amplify the signal to the required level. And then we filter this data, and you can see in 3 that we have the same modulated data that we transmitted here. We have it here, and then we can demodulate this data using the demodulator on the board to get to the data that we transmitted at the first place. So after we gathered the information that we transmitted, we can log this on the SD card, or we can transmit it using LoRa transmitters. So as a result, this project is a work in progress. We developed 2 evaluation boards for the telemetry system. We achieved 40 bits per second using the hydrophones that we used, and we are trying to improve the communication speed to reduce the power consumption and miniaturize the design. Range tests are also in progress. We also integrated our sensor with a novel electronic tongue sensor to measure the water parameters such as nitrate and phosphate. And this novel sensor is developed by Unitov, our project partner in the IMPAQT project. So, in conclusion, the IMPAQT telemetry platform can replace the existing sensors cables in underwater environments, in aquaculture, in IMTA sites. It provides a communication platform for underwater sensor network, and also it provides a real-time communication where it can be used in robotic system, in automation, and in divers even communication for safety purposes. So future work involves in further miniaturization of the transmitter and receiver board, so it makes it possible to develop a smaller sensors, and it also make it possible to develop a smart underwater personal communication system. Just imagine a band on your hand that you can transmit information and you can communicate with the other divers, let's say underwater. We can improve the battery life, and this will enable us to collect information for longer time period. We can fabricate a higher frequency piezo transducer, and this will enable higher bit rate and lower power consumption. And we can implement different demodulator on the board to improve the communication speed and noise resistance. And we are working on integrating with more commercial off-the-shelf sensor and research-based sensors. And also we are trying to make a system on module, so you can just basically buy this module from the market and connect it to your sensor to collect the sensor information. Thank you so much for listening to this presentation. If you have any question, I would be happy to answer those questions.